Okay, so we're going to look at some derivations of the natural frequencies of simple harmonic oscillators. One of the more common ones to look at is a mass going up and down on a spring. Now, to do the easy derivations, more or less, for the natural frequencies for simple harmonic oscillators, we must bring in the equation that defines a simple harmonic oscillator. That equation looks like this. Omega squared times x plus x double dot equals 0. Now, as we talked about in class, omega squared is a constant squared, and it is specifically omega, our natural frequency. It is multiplied by the position as a function of time, and then we add that to the acceleration as a function of time. In case you've forgotten or you weren't there for that day, the dot notation means specifically a time derivative. So another way of writing this would be d squared x dt squared. One dot would be for one derivative, two dots is for two derivatives, three dots would be three derivatives. So x is our position as a function of time. Technically, I can mark these that they are functions of time. X is position, x dot would be our velocity, x double dot would be the acceleration, and x triple dot would be the jerk, and so forth and so on. All right. So for this, what we really need, we can find the natural frequency of a simple harmonic oscillator, if it is a simple harmonic oscillator, by finding something that describes its position and adding that to something that describes its acceleration. And if that agrees with this equation, then it is a simple harmonic oscillator. Now broadly, we talked a little bit about this in class. I had you all think about a function that if you take two derivatives, you get more or less that function back except a negative. So we would have this, take two derivatives and add it to itself, so we would get pretty much the same thing back, except with a negative so that they would add to 0. The solutions to that, at least some of them, would be sine. So sine of theta, if you take the derivative, it becomes cosine of theta. And then chain rule, if you have a coefficient in here, then one term would come out. The derivative of cosine. Cosine then goes to negative sine. So if we start with sine, take one derivative, we get cosine. Take a second derivative, we get negative sine. The same thing, almost, back, except with a negative so that they can cancel each other out, getting 0. Sines and cosines are the motion that you get from simple harmonic oscillators. And we've seen a little bit of that in class. I may have some video type stuff that I can supplement with it. That being said, we've identified that a mass on a spring should act as a simple harmonic oscillator, but let's find out what the natural frequency is, which means I need to have some relationship between the position and the acceleration. On the upside, for a mass on a spring, let's say that we're at some nondescript point here, and we're some distance away from equilibrium, where that would be a position of 0. All right? So, I apologize. Let's do this in the simpler format. Let's do this as a level one on a frictionless surface so we don't have to worry about gravitational aspects. If I have time, I'll make a video related to gravitational aspects, but we'll find that the numbers end up working out perfectly, that you can almost ignore them as long as you use the new equilibrium position and not the natural length of the spring. All right. Let's say that this is x equals 0, and over here we are at x equals some positive number. Over here we would have x is less than 0. Over here we have x is greater than 0. You'll see why that becomes important here in a little bit. However, let's do the main thing that we would normally do while trying to solve a system in which things are changing how they move. We're going to turn to Newton's second law. Specifically, we're going to look at the sum of forces in the x. Well, for this object, the sum of forces in the x direction are going to be the spring force. So I'm going to have spring force. And since that is my only force, force. I'm going to set that equal to my mass times my acceleration. All right, so here's where you can fill in a few things, but my x position is actually positive, but my acceleration is actually going to be negative. The force is going to be pulling it back this way. So when I replace the spring force, we'll use something that I taught you all last semester, negative k. Normally I write delta x, but I'm just going to leave it as x. I always had you learn it as delta x because we would always take a displacement from the equilibrium position. Well, since we're setting in this x equals 0, if I'm at equilibrium, I'd put in x equals 0 and I'd have no spring force. The other nice thing about this is I can use this to define exactly where I am. If I'm at x of positive 1, I'd put in positive 1 and I end up with a negative force. If I end up at negative 1, I put in negative 1, the two negatives cancel out, and we end up with a positive force because the force would push it back this way. In short, while I taught you delta x, it was to help emphasize that there must be a displacement from the equilibrium point, and originally the natural length of the spring, which does apply in this problem. We do want to keep this negative. It's important. You'll see how it turns out. But most importantly, it sets up a fundamental thing that we need for simple harmonic oscillators, namely something called a restoring force. If I move this object to the right, the force is to the left and tries to restore it to where it started from. If I move it to the left, the force is to the right. The force is always trying to push it back to where it came from. And so, whatever my position is, positive or negative, the force will be opposite of that. All right, let's fill these in. For the spring system, this actually goes very quickly. You're going to see that we're going to be done pretty quickly. So I end up with negative kx equals ma. Okay, well, I'm going to add kx over here, and I get the following. 0 equals kx, order doesn't matter, plus ma. Remember our general equation. We need omega squared x plus a equals 0. Omega squared x plus x double dot, which is the acceleration, needs to equal 0. I could write the equal 0 over here. But hopefully you see where we're going. We've got, hey, look at that. There's x and there's a. I've got an m next to a, though, so what I'm going to do is I'm going to divide everything by m. That cancels that out, and 0 divided by m, assuming the mass is not 0, any 0 divided by any finite number will end up being just 0. So I get the following. 0 equals k divided by m x plus acceleration. Writing this a little bit differently, k over m x plus a equals 0. And then bringing in our defining equation, omega squared x plus a x double dot equals 0. We now know that from these two equations, omega squared must equal k over m. So omega, the natural frequency, is the square root of k divided by m. There's the derivation for the natural frequency of a mass on a spring. We simply need a relationship between our position and our acceleration. There'll be a subsequent video in which I show you how to work with the pendulum.